All right. Welcome those of you who decided to stick around this week. We're going to finish up QR factorization discussions today and talk about why we care about the matrix norm, stability, convergence, things of that nature for the problem AX equals B, and kind of why we care about that type of thing. And we might get to eigenvalues today. I don't know. It'll be exciting to find that out. The homework, of course, is due next week. The last homework, I'm going to give you a week to do, and I'll just shorten it a bit from usual. So I will release that at the normal time. And then there'll be a final review, and the final will be over the weekend after the last class, which will be a final review. So that's the plan for the rest of the semester. Are there any questions? Yes. That I do not put? Sure. Yeah. I could put them on the final review, for instance. Any other questions? Yeah. If you have a conflict for that weekend, let me know, and we can adjust it individually. I'm a little, I don't want to change it for everybody because it's already been announced at this point, so people have made plans. And the other advantage of doing it early means that it's done and you don't have to worry about the class anymore, so a little bit earlier. But if you do have a conflict, just let me know. Any other questions? All right, yeah. But it's because it's by a guy named Householder. He came up with it, and it is triangularization in the sense you're trying to make an upper triangular matrix.
No, it's just bothered by Householder.
Oh yeah, no, it's a guy's name, I think. I don't think it's anything more complicated than that. Yeah. Any your questions? Eigen is not a guy's name. That is a German word. One of the small little pieces. Okay, so just to kind of finish off our discussion of QR, we've kind of gone over 3 different algorithms for computing QR. They all should give you analytically the same result, but we do see that there is some computational advantages for each of them. So usually if you asked, say, NumPy to compute QR factorization, it's going to use Householder triangularization or something, sometimes a little bit more fancy, but that's the basic algorithm that's going on behind the scenes. One of the applications of QR, and we'll see another one when we talk about eigenvalues, is to just solve AX equals B. So we know if we have a QR factorization that we can break A into Q and R. So why does that matter? If we plug in QR for A in AX equals B, what's going to happen? What good thing is going to happen for us? So we have this. What advantage? Why would we want to do that? Because this takes effort to do. Why would we want to do that? Yeah. Yeah. So Q transpose is the inverse because this is going to be an orthonormal matrix. All right, so we multiply both sides by Q star, Q transpose. So we can definitely do that, which means that we get Rx is equal to Q transpose Q star B. So why is this advantageous?
R is an up triangle matrix, so find it in the equation.
Right. So that's exactly it. R is now in an upper triangular form, which means we can do backward substitution. So that just refers to, let's see if I can find a better marker. So R looks like this. So we have things over here. You know, who knows what's in here? I don't know, stuff. But there's one value down here, which means that if we have our vector x, so x m down here, this means that some value times xm is equal to q star b, which we also know is just a vector. All right, so then we can solve for this xm, and then we can solve for xm minus 1 and xm minus 2, so it's backwards substitution going up. So that's always the goal for doing these types of things. We want to get something in upper triangular form, or lower triangular form, note, would be the same type of advantage. We just start from the forward direction, go downwards. Okay? That's the advantage of QR. We have a backward substitution to do. This is very algorithmic. There's no issues with it. So once we've figured out how to do QR, we can do backward substitution. And we're going to come back to this example a little bit and talk about whether that's a good idea or not. The other kind of big application is the least squares problem. So we know that in some instances, maybe B doesn't live in the column space of A. Right? That's what the problem is. But we want to minimize perhaps the difference between these two things. So that would be kind of the least squares problem, or minimize the difference between those two things. So what does this look like? Well, one way to look at it is that we have the range of A, or the column space of A. So this is just a one-dimensional version of this. B doesn't live in it, but I can look at the quantity that is in the range, so I can project B onto the column space, right? And then I solve this problem, right? I just replace B with Y, and I can do that because I know that Y lives in the column space, or the range. So this is what this thing looks like at that point. Okay? And we call the R, this difference between B and Y, the residual. That just means how much could we not take into account. So it's the orthogonal component to the column space of A that B needs to also be a component of. So to do this, we can do the exact same thing. We take the QR factorization of A, and we know that there's a projector, QQ star, and Q is supposed to be an orthonormal basis of the column space of A, at least the reduced version of it is. So this projection is going to be the projection onto that column space, which is exactly what we were looking for. So another way to look at the normal equations is that we're actually forming a projection. Exactly what that is. So if we just start plugging things in here, we get A star A, that becomes R star Q star, because the transpose, if you take it inside, flips the order of operations. We do that on the other side as well. So we get R star QR. So Q star Q we know is just the identity. We get R star R, X is equal to R star Q star. And we end up getting, again, something that looks like Rx is equal to Q star B. So after everything is done, we actually come back to the exact same problem. And the way this all works is because we have this projection that's kind of lurking in the background. We're looking at how do we actually take B and project it onto the column space and then solve that new problem. It's a very similar thing. And of course, here we again have backward substitution working for us so that we're going to be done. Okay. So once we really find the QR factorization of matrix A, regardless of what's going on, we can solve both problems. We're okay with what's going on. And it's a simple operation. Now this being said, we don't necessarily want to do, if you really wanted to just solve AX equals B, there are other ways to do it. If A has special properties, that's going to be a homework question for the next homework. So things like Cholesky factorization and LU factorization, where you're also factoring the matrix into two pieces that gives you something similar. So if you want the exact solution to AX equals B, that's the way we kind of do it. So it's a play on basically Gaussian elimination, like that. So, but QR actually is nice because we can get more information out of it. It actually does have stability properties we like, so we saw that it has some computational advantages. So in practice, we often do use this if matrix A is generic. So we always know we have a QR factorization for A. Any questions about QR? All right, so ever onward. Is this so wobbly? There we go. Okay, so we've talked about something like stability before. This is we're going to be talking about it again. This is a very similar type of concept. Conditioning isn't something we've said before, although we have talked about stiffness and things like that. It's a very similar type of concept. So conditioning and stability really talk about two different parts of a problem. So here we're thinking of, well, there's the problem itself. I want to solve ax equals b. So the conditioning refers to whether that was a good idea. That problem can be really, really hard. And that's independent of trying to solve it numerically. Okay, so that's the conditioning. The stability talks about the algorithm we're using. So together, we kind of expect conditioning and stability together to actually give me a good answer. The answer I want, or something that I expect to behave correctly. So we're going to go investigate this a bit. So keep in mind that there's going to be, stability is referring to the actual algorithm, conditioning is referring to the problem we're asking. So just the mathematics of what's going on. Okay, so there is an idea of conditioning. If you've taken PDEs, you've probably seen this before. There's an ill-conditioned and a well-conditioned problem, or an ill-posed or well-posed problem. This is a very similar type of idea. So a well-conditioned problem is one where a small perturbation to the original problem leads to only small changes in the solution. Okay, so this is exactly the same definition throughout mathematics of a conditioned problem. So basically, you perturb the input. Does it blow up, or does it go like crazy? This is a relative type of thing. You can put lots of mathematics around this. Like if you perturb something, can you bound it in some neighborhood? That's the kind of things we're talking about. Similar things exist for linear algebra problems, and that's what we're going to use for conditioning. All right. So just to kind of be a little bit more abstract for a little bit, we have some function f, which takes x to y. So some space x, some space y. In our linear algebra case, these are going to be vector spaces. We have, the fun epsilon. There could be deltas in here if we really wanted to. But the idea is that the difference between some perturbation to the input, so that some norm in here, is going to be bounded by some constant c times the norm of the input. Okay, so you see this for convergence all the time. You see this for continuity definitions, and you can have c be dependent on epsilon that has different properties or different conditionings. But that's the type of thing we're talking about. Somehow we can bound the change in the solution by the change in the input. Okay? All right, so get a little bit more concrete. There's the absolute condition number. So this is going to look something like this. We have this is lowercase delta, is going to be defined by x plus epsilon, so epsilon is some small number. We're going to say that's a small perturbation to the input, and that delta f is going to be the result of the difference between that small input change and f, the original input. And we're going to say the absolute condition number is going to be the supremum over all the delta x's, small, such that delta f over delta x in some norm is going to define that condition number. Okay? So really we're just saying, okay, so take delta x, find some bound on this. This is really kind of getting rid of or abstracting away that c. So the condition number in some sense is defining that c. So it's a little vague here, and it's purposeful. We'll see a much more concrete version of this. Note that this is suggestively looking like a matrix norm at this point, and it is going to become a matrix norm. That's why we define it that way. But at this point, we're just going to say delta f and delta x are going to be infinitesimal. So some sort of derivative should be kind of reminded here. Okay, so we have some delta f over delta x that has something to do with a derivative or derivative-like thing. And in fact, we can relate it to that. So if we're talking about a condition number of a general function f, and f is differentiable, we can actually, regardless of this thing being a vector or a matrix or whatever, we can actually find the Jacobian of this thing, and we can use the Jacobian of this to define the condition number with the delta f approximately equal to the Jacobian times delta x, and we find out that the Jacobian, or the norm of the Jacobian, is going to be something like the condition number. So this is for generic f that just happens to be differentiable. So very generic condition number type of definitions. So this is another idea, and actually this is the one we're going to use because absolute errors can be a little bit difficult to kind of get a hold of. What is the proper thing to compare it to? So we're going to use relative condition numbers. The relative condition number looks a little bit more complicated, but we're basically normalizing the infinitesimals by the value of the function, and the infinitesimal in x by the value of x. So this gives us a little bit better handle on exactly what the size of the condition number means. So note that the absolute condition number had a hat on it. This condition number does not, and that's purposeful because we almost always use the relative condition number for these things. We're still taking the supremum over delta x, so we do have to be a little bit careful on how we define things, but recall that delta x does have x in it. So that stuff actually all is still behind the scenes here. Okay, so if we plug all this stuff in, we replace the delta f's and the delta x's, we find out that we can actually define the condition number by the Jacobian, the norm of the Jacobian. So the Jacobian, remember, is a matrix. So keep that in mind. There's a matrix norm in here already. Divided by f of x, the norm of f of x divided by the norm of x. So in the cases these are just scalars, this would be the derivative over a scalar divided by a scalar, right? So something that should be something familiar. Okay, so let's just actually put this into practice real quick. Calculate the relative condition number of square root of x for x greater than 0, because we don't want to deal with imaginary numbers. Okay, so see if you can figure out the condition number for this particular problem using that definition. So I'll leave this definition up because that's what you got to use. So give it a whirl, and we'll discuss kind of the implications of this one. All right, so let's just construct this thing. Again, the Jacobian in this case is going to be just the derivative of square root of x, which is 1/2 times square root of x, like that, right? So we're just going to form this thing then. So we have kappa is going to be equal to 1/2 square root of x divided by square root of x times x, like that, okay? And as you see, if we actually are a little bit careful about this, oops, this would be a division. All right, we get the square root of x gives us an x. This x goes up above, they all cancel out, and I end up getting 1/2. What that means, I don't know, it's just 1/2. It's the relative condition number. So not a large number is really what we're going for here. And in fact, for going through this, we do have to be a little bit careful. The fact that I had x is greater than 0 is important because if I actually was taking norms, I do have to use absolute values for all of this stuff. But because I didn't have to worry about negative numbers and all this, I can just get to this point, okay? So do be aware of that the condition number always has to be positive, first of all, and we want it to, even in the scalar case, work out to be that way. The other thing, too, in a heuristic sense, you probably want this thing to be near 1. Like 1 would be perfectly conditioned. And I'll show you another example why that might be the intuition here. But really what we're looking at is the Jacobian divided by the ratio of f of x over x. So somehow something that looks maybe like approximation to a derivative and a derivative, if those two things are about the same ratio, they're changing the same way, that'll give us something that's well conditioned. The problem is changing in the input and the output at about the same way. Okay, so here's a little bit harder example. So this is a scalar-veiled function, but it has two input. So it's taking R2 and mapping it to R1. Okay, so try to figure out what the Jacobian is in this case. It's just vector norms in this case, and we'll do an example with L infinity. So that's the max norm for the vector, the maximum value of the absolute value of all the elements of the vector. Okay, I'll give you a couple minutes for that. Okay, so the Jacobian in this case is going to be a row vector, and that's because f only has one value, so we have just df1 to go through, so it's going to be equal to df dx1, comma df dx2. So this is important because this is still a matrix norm in some sense. So when we're using the L infinity norm, we have to sum and find the maximum, but there's only one row. In our particular case here, we find that this is going to be equal to 1, negative 1, just from x1 minus x2. So if we kind of go through this, we have the Jacobian. This part is a little bit trickier to understand why this is happening. We know that the J infinity norm is going to give us equal to 2 because this is one row. The max of the xi's is going to be the L infinity norm of x, this bottom part, and then this thing is going to be the L infinity norm of f of x for all of that. So not so trivial. It's going to depend on what x1 and x2 are because of the maximum and then the difference here. So in particular, if x1 and x2 are really, really far apart, we could actually get a small condition number, or we could make this kind of arbitrarily large as well. And so that's kind of the tricky part about this. Usually it's going to depend on the inputs, so be aware of that. Finally, matrix vector multiplication. This one is, of course, going to be something more akin to what we're interested in for our linear algebra. But this is a very simple operation. It is a multiplication just of a vector and a matrix. Okay, so when thinking about this problem, think about it that way, and think about the fact that the matrix is constant. Okay, so I'm going to give you a couple seconds to just think about that, and then we'll go through the actual kind of construction of how we figure out the condition number here. Okay? Okay, so we kind of have, you can do this two different ways. You can look at this as actually a function, and you can find the Jacobian of this thing. It is just a set of vectors, so it gives you back out a vector. So we're mapping to a vector, and we're putting in a vector, and A is just the function that's mapping between the two, so we can find the Jacobian of this thing. But I want to go through a little bit different of an idea, and that's kind of going back to our original notation here. So the fact that I'm only perturbing x is the input. We're going to come back to the idea of actually perturbing A as well. So A could be an input to the algorithm, which is how we're going to look at it. But let's just concentrate on x. So we have x plus delta x minus ax. So this is just by definition of the relative condition number at the top here. If we simplify this thing down a little bit, to kind of get rid of some of the complications, we see here the supremum of delta x, a delta x over delta x is still there, okay? But we can actually associate that with the condition number, or excuse me, the norm of a matrix, an induced vector norm of the matrix. So we get A, and this is in fact going to be, can be bounded by above by the condition number of A inverse. Excuse me, I keep on saying condition number. This is the norm of the matrix A inverse. So we can actually bound the condition number by the norm of the matrix A times the norm of the matrix A inverse. Okay? That's why we care about matrix inverses, or excuse me, norms of matrices, is that they're telling us things about the conditioning of the problem. So what matrix norm you put into here depends on what question you're asking, of course. You can get very different things. For instance, if you were going to use the L infinity norm for this matrix norm, you'd be talking about like what size the columns, or excuse me, the rows sums were, taking the maximum of those, or maybe using the L2 norm. So what's the maximum values that are coming out of this thing, so the eigenvalues. And then A inverse is going to be the inverse of the eigenvalues. So you see kind of like, all right, well, the biggest and the smallest eigenvalues, what are the ratios between those two things? And that's why we get a condition number in that case as L2. So we're going to keep on bringing this all back together, seeing why we care about this particular definition. But this is just for matrix vector multiplication. So very, very simple operation we want to be doing. So we actually say that the condition number of a matrix is defined as this matrix norm of A times the matrix norm of A inverse for some norm. Okay, it just has to be a norm. So this is for some generic A that's going to be applied to a problem. And we have this general sense that if this kappa, this relative condition number, is small, then A is well conditioned. Whatever the mapping is going to be well conditioned. If A is singular, so we can't invert it, which means I can't actually evaluate this thing, we assign the condition number of the matrix to be infinite. Okay? So this is starting to say something about whether or not A is invertible. Is it a nice matrix? And in fact, this also is going to give us something. If A is really hard to invert, this number is going to be very, very big. So again, like some idea of how hard the problem is to solve. So this is an example. If we're using the L2 norm, we can write the condition number as the spectral radius of A transpose A. So this is the eigenvalues. It has to do with the largest eigenvalue. You take the square root of that. That gives you the L2 norm of the matrix A. We have that over the same thing, but the inverse of that same matrix. So this ends up being the maximum, square root of the maximum of the absolute value of the eigenvalue divided by the minimum. So if you recall from when we're talking about ODEs and stiffness, we had a very, very similar type of idea of what stiffness was. It was the ratio between the maximum and the smallest eigenvalues of that matrix that define the ODE. And we have the exact same thing here. So these condition numbers and stiffness are really very similar types of concepts, at least for the L2 norm. And that's exactly what we're often interested in. OK, so let's make it a little bit more complicated. That was just focusing on A and somewhat predicated on the idea we're interested in multiplying A times X. Now we want to say, I want to solve a system of equations. So let's define a condition number based on that. In this case, we're going to say B is inherent to the problem, but I can, the matrix A and the vector X are both input. So I want to get back out B. Okay? So what does this mean? All right, so we're going to perturb both. So now I'm going to do some algebra. I just expand this out, being careful of order here. I can say AX is equal to B, because that's what I want. So these two terms cancel out. We still have the delta AX here. A times delta X stays here, and then we're going to say these two things, because they're both infinitesimal, is too small. We just throw it away. Okay? So this is kind of what we're left over. We have something X and A that are not small in the sense that we're defining. And we can solve for delta X from here. Right? That's just sticking the right term into the right-hand side and solving a little bit. And we end up getting that thing is going to be equal to negative A inverse delta AX. Okay? So if I take the norm of both sides, okay, so using some inequalities, I can break it up like this. So the norm of this delta X is going to be less than or equal to the matrix norm of A inverse times the matrix norm of delta A times the norm of X in general. So we have a lot of pieces to the condition number we had already specified. And in fact, if we rewrite this thing, we can rewrite it like this, such that this ratio is less than or equal to the A inverse times A, just from doing this and multiplying both sides by the matrix norm of A. So this implies this. And of course, we know that that's already equal to our definition of the condition number for the matrix A. So in fact, not only is this the condition number of the matrix A times X, this also gives us the same condition number, same type of definition for solving the problem AX equals B. Okay? So the matrix norm of A times the matrix norm of A inverse provides us some idea of how hard it is to solve the problem AX equals B. So there's lots of different theory, lots of different ways we can go with this. I'm going to just highlight a few different ideas. So if we have B be fixed, so I didn't actually perturb B. Let's kind of let that go. You can go that way. It just becomes more complicated. But we have B fixed. We're considering the problem of computing X in AX equals B, where A is square and non-singular. So we kind of have to start from there. The condition number of this problem with respect to perturbations of A is the condition number of the matrix kappa A. Okay? So this is just stating what we already found. We think that the condition number, we can actually show, if you really go through all that, that was a little bit hand-wavy. We can add the supremum back into this thing. But the condition number really does actually give us the correct thing for this type of problem. Are there any questions about conditioning before we move on to stability so far? All right, so condition number, completely in the realm of the question we're asking. It's the mathematics, it has nothing to do with numerics yet. Stability is numerical, okay? So if we have a well-conditioned problem, we might expect that we can solve it numerically. If we don't have a well-conditioned problem, we expect that we're going to have issues in the ideal sense. So stability is really getting at the first idea. So if we have a well-conditioned problem, we expect to be able to have a good solution to our problem numerically. Now, we actually might be able to expect something even if it is ill-conditioned, but we need to be careful. So we want to actually quantify what we mean by these ideas. So as we saw before, we had this idea of error, absolute error and relative error. In this case, just a simplified notation, the capital F is going to be our numerical approximation. So in some sense, this is the algorithm answer given the same input. So we're going to start changing the input and the output. So capital F, algorithm given exactly the same information. This is the true solution to the problem that we're asking. Okay? So we can define the absolute error and the relative error just like that. That's not anything different. We're just putting norm bars on this now. So it can be in some norm that we like. And in the ideal case, we'd like the relative error to be machine epsilon. Or we should be able to get to machine epsilon given enough numerical effort. Okay, so there's two types of stability in these cases. A forward stable algorithm for some input space, so x is going to live in some input space that's defined. A forward stable algorithm has this exact property. So at some point, we can get to this. All right? So it's convergent. This is just another way to say something is convergent. More importantly, because we've seen this already, this idea, a forward stable algorithm gives almost the right answer to exactly the right question. That's a very convoluted way to say, if I have a forward stable algorithm, I will make some error. I'm always guaranteed to make some error. I'm on a computer, right? But I'm going to give almost the right answer to exactly the right question, which is referring to the input is exactly x. Now we know that that also is an issue. So although this is great, we do need to be careful. But this is the definition of forward stability. So keep this in mind, and we're going to come up with another statement that's even a little bit more mind-bending in a little bit. And that has to do with backward stability. Okay? We had forwards, now we have backwards. Backward stability is a stronger notion of stability, and it's really getting rid of this idea that we have exactly the right question. Okay? So we have capital F of x, and we're going to say f is backward stable if f of x is equal to f of x hat, where x hat is not quite x. Okay? So this is really weird. So if I'm asking the question fx hat, which wasn't the original question I want to ask, my algorithm actually gives me the right answer to the original question I really meant to ask. It's just like, okay, well, that's odd. All right, so we have some x hat that's almost x. It's machine epsilon away from x. This is, maybe we could do a little bit better than this. We know floating point precision might be able to be better, but we're going to stay with this because you don't know where x is coming from. X is the thing we actually want to ask, so it's the input. X always is going to describe the input. So this is how we say a backward stable algorithm works. It gives exactly the right answer to nearly the right question. So somehow it's figuring out that you didn't answer the right question. There was some perturbation of the right question, but you do get the right answer back out. So obviously we want backward stable algorithms because that would be nice. As in the forward stable case, although that's also nice, we are not guaranteeing that if we do have a perturbation to the input, that we're going to get the right answer back out. That is not necessarily given. Yes? F of x hat. F is the true solution. So whatever this ends up being is the true solution. X hat is some perturbation to that. That's on the order of machine epsilon in our algorithmic sense. You could say this is epsilon too, or just some difference like that. Does that make sense? Somewhat? So actually, this is really important, and combining this statement with the last statement is kind of a key step in understanding why this stuff is kind of key to knowing why forward and backward stability kind of go hand in hand. So I want to give you about a minute, and if you're sitting next to someone, try to explain it to them what it means to you. Like, why is this even possible? Because this seems a little magical, right? It knows somehow the right thing. But try to come up with an example where this might be true, or something that might suggest why you could get this to work. Okay? So I'll give you a minute for that, and then we'll start discussing a little bit more concretely what this means. So one example that I like to think about actually comes back to ODEs. If you have an ODE that you're solving, say in kind of like it's a two-dimensional ODE, and you know that there's a stable point, right? So if you have like a phase plane, looks like this, or even like a ODE system of ODEs with a limit cycle, we're on the phase plane, then if this is a stable point, then even if I perturb away from this, I start over here, I know I'm going to go back to that point, okay? So that's a similar type of idea. We want algorithms that even though I'm going to start at some perturbation to the original thing that I was trying to get at, it's still going to force me back to that point. So that would be a backward stable type of idea, okay? So keep that in mind. So this statement and the statement before, we can combine, though, to get the following. If we have capital F of x minus fx hat divided by fx hat. So somehow we're talking about the relative error with respect to the perturbation to the input for some x hat. We're going to say something that's going to be stable. So both backwards and forwards stable will give us some idea that a stable algorithm gives nearly the right answer to nearly the right question. And this is really what we aim for. We really can't get backward stable for most cases, but we can get this. And this is what we really want to do. So in other words, if we perturb the input a little bit, we only perturb the output a little bit. That's an algorithmic idea. It should sound very familiar to the condition number. So the condition number has a very similar type of idea as well. You perturb the input a little bit, you perturb the output a little bit. Okay? We have the same thing on the algorithmic side. We want to have the exact same idea. Okay. So putting both these things together, we have the condition number, which talks about the problem itself, and we have the algorithm, which talks about the stability. And we have the following theorem. We have a backward stable algorithm, and it's applied to solve the problem f taking x to y with the condition number kappa. Okay? And we're on a finite precision machine. We have our numerics. We're approximating things. Then the relative error satisfies this expression, where notice that in the bound on this thing, or the equality here, we have the kappa number times machine epsilon. So now, if kappa is big, it might actually overcome machine epsilon. Even though we have a backwards algorithm, we still have to have a well-conditioned problem, or we're still out of luck. So if kappa is 1, for instance, we're OK. So that would be good. One example that I think is illustrative, if we have ax equals b, if a is the identity, that's a really trivial problem to solve. X is equal to b, right? The norm, the matrix norm of the identity is 1, whether it's A or A inverse, because A inverse of the identity is still the identity, which means the kappa is equal to 1. So the easiest problem to solve, the identity times x is equal to b, gives us kappa equal to 1, which means that we get machine epsilon back. So that's why the condition number being equal to 1 is kind of considered the best case scenario. And we also see that the multiplicative piece of this is important as well. So we need both conditioning, and we also want stability to get back out something that talks about the error. Okay? So that's really what we're trying to get at. The relative error here is going to be equal to something machine epsilon times kappa. Okay? So this is a little bit different than what we've talked about before, where we have some sort of truncation error. We don't have truncation error in this case. This is just talking about being on a finite precision machine and how hard the problem is to solve. Okay? It's a little bit different. So we can prove this pretty easily just by combining our two definitions. So we can bound by the backward stability idea this piece with kappa plus machine epsilon times x hat minus x over x. So this is all coming from the definitions. And also we know that this has to be equal to that just by definition as well. So it actually is basically a one-step type of thing just by definitions. So keep that in mind. This is a fairly straightforward idea once you have the condition number and this idea of backward stability. Just to kind of close off this particular discussion, there's related to backward stability and forward stability are these ideas of error analysis in both the backward and the forward sense. Backward error analysis is the process of using the condition number of the problem and stability of the algorithm to determine the error. I've never been particularly comfortable with the fact we call it backward. It's more thinking that you have the algorithm and you're trying to say the algorithm is going to give you some sort of idea of how close to the answer you're going to get, along with the difficulty of the problem, and just trying to work backwards from there. The forward error analysis is much more similar to what we've done already. So especially for ODEs, we're saying, okay, I'm going to watch my algorithm, and I'm going to watch the error accrue and just keep track of it. So like when we're doing time stepping, that's exactly what we did. We were doing forward error analysis. And we're counting up the error, making sure that the error didn't blow up. And then at the end, we see, okay, so if I slightly perturb the input, we can talk about what the error is going to do. So that was what we were doing before. Okay. Backward error analysis is, then neither of these are better or worse than the other. It's just they're just different tacks on the same thing. All right, so let's actually apply this. So let's apply it to stability of AX equals B, and we're going to use householder triangularization. So first of all, we know that we have a condition number for AX equals B. We've already defined that. But we're now going to talk about the stability of not only householder, but also solving the problem AX equals B, because there's a few things that are going into this. So we're going to use QR factorization. So let's talk about that first. So if we have a QR factorization, and we're computing it via householder triangularization, we can actually state that Q hat, R hat, so this is going to be the finite arithmetic versions of these things, the approximations, for A plus delta A. So we're going into this idea that you might have some perturbed A. It's not quite the original A we want. And that's why we have this bound. We're saying the perturbation can only be machine epsilon size. Then we can actually say that householder triangularization is backward stable. This is not exactly trivial to show, but it is actually the reason why we actually prefer householder triangularization, because the other versions of QR that we saw are not backward stable. That is the main problem with them. So if we have that, we still need to solve AX equals B. So we saw how we did that in just writing it out. But we do need to figure out whether or not we're losing some sort of stability criteria here. So let's actually investigate that. There's a few steps here. We're going to compute the QR factorization of A. We know that's backward stable. So small perturbation in A gives us only a small perturbation in QR, and actually gives us the real QR. We're going to multiply both sides and B by Q star to get Y. So we're doing that projection onto the column space of A. And then we're going to solve using backward substitution. So these are just the steps we do to solve AX equals B using QR. We know 1 is backward stable. We just had a theorem about it. The matrix vector multiplication, well, we can write this estimate of the backward stability doing the same thing we did before. We perturb Q. So we're going to actually say, even though we have some approximation to Q, we know that's going to be backward stable. We don't know overall. We have some Y. It's also a perturbation. And that's going to be equal to B. I say we're not perturbing B in this case. So we already know that this is going to be machine epsilon by the fact that it's backward stable. We're going to invert this matrix. We know that is going to be unitary. And because we know that matrix vector multiplication is also backward stable, we just showed it actually. We know exactly why it is because we calculate the condition number. Then we can actually say that this is this vector B is going to end up just being a slight perturbation of the input as well. So it's really just talking about matrix vector multiplication due to the fact that Q is actually unitary. That makes it a lot easier. Otherwise, we'd have a little bit more of a problem here. The third step is backward substitution. We do a very similar type of operation where we perturb R. We look at X hat, Y hat, which are perturbations, again, of the original X and Y. We know that because of the definitions of backward stability when we're calculating R and just perturbing these things, that we require this to be machine epsilon. So then if we just do the problem in reverse, we end up seeing that, again, we're going to get something that's going to be slightly perturbed. So again, machine epsilon different from what we actually ended up with to begin with. So putting this all together, we know that QR factorization can solve AX equals B. Each of those steps is backward stable, and so therefore the actual solution via QR can have, we can say this statement, A plus delta A, that should be little delta, X hat is equal to B, so that would be slight perturbation to the input. If we require the input to be machine epsilon, the perturbation, then we can say that the above algorithm satisfies this, which implies that the answer we're getting out, because X is actually the answer where we want, is also going to be within kappa times machine epsilon. So using QR, we can figure out that this is actually a backward stable algorithm for solving AX equals B. So again, I do want to stress, it's not just the algorithm itself that matters here, it's actually also kappa. We need to make sure kappa is going to be small for this to all work. So if kappa is 10 to the 16th, machine epsilon is 10 to the negative 16th, we're going to order one error, which is no good. We don't want that either. Okay. So that's the discussion of stability and conditions. This is why we care about matrix norms. Oftentimes when you hear somebody talking about, I have a big linear system to solve, they will be talking about the condition number of that matrix as a placeholder for how hard the problem is to solve. This can come in all sorts of ways. You can estimate these things based on the eigenvalues, but that is very core to a lot of numerical methods, understanding what AX equals B, how hard that problem is to solve. And you can easily get condition numbers in the 10 to the 26th, like just gigantic numbers. It's not that we still don't want to solve that problem, it's just going to be a lot harder. So we're going to actually show some other ways to solve these things in other situations, but just realize this really is a problem. It's not trivial. Kappa can often be gigantic. And so unless you're going to a higher precision, which is also an option, you're kind of, you gotta figure out something else to do. Okay. Are there any questions about this before we start on eigenvalues? Okay. Let us do that. All right, so we're trying to talk about AX equals B a little bit. There'll be more in the homework. Kind of the last problem we want to talk about in linear algebra before we loop actually back around to AX equals B are eigenproblems. So let's kind of think about this a little bit. Of course, we have AX is equal to lambda x. This is the generic version of the eigenproblem. There are other ways to formulate this. But this is the basic idea. So we have x, the vector, and we talk about the set of all eigenvalues as being the spectrum of A. So this is coming from more of a continuous, maybe operator idea. Operator also has spectra from the functional analysis standpoint, which is interesting ties to this, but we will not go through that. We also know that in order to find the eigenvalues, you usually have to solve a characteristic polynomial. As we said earlier, this characteristic polynomial is defined by the determinant of zi minus a. So z, the roots of this thing, z, are going to be eigenvalues. Okay? Now, we all knew this. This is basic linear algebra. And we have this statement. Lambda is an eigenvalue of a if and only if it is a zero of the characteristic polynomial. There is no other choices for that. Seems obvious, or we make it like this is a statement of definition. This isn't so trivial. I mean, these are very different things. It just happens to be that these are actually equivalent problems. So that's what I'm trying to stress. Finding the eigenvalues of a matrix A is equivalent to finding the roots of a polynomial. So we know something about that. We've talked about it a bit. And one thing we did when we were finding roots of a polynomial is we used iterative schemes, which is in contrast to some of the other things we've done. Now, why is that? oh, well, here's a proof of this. It's, you can look at that later. It's not very interesting. Hopefully you've already seen this idea from that. I guess I'm going to take a little detour here. Or did I skip something? Felt like I had something else to say about that. Okay, well, apparently I don't know my lecture notes well enough. Okay, so eigenvalue decomposition. This is one of the decompositions we're going to be interested in. So A is equal to x lambda x inverse. X is going to be the matrices that have the eigenvectors as the columns. Okay, well, all right. This is basically the matrix form of the eigenvalue problem in the first place, because if you put x inverse onto the other side of this thing, multiply both sides by x, I get A times x is equal to lambda times x. So lambda just has the eigenvalues down at the diagonal. So we can't always do this, just to be clear. We have to have a full eigenspace. Full eigenspace refers to the idea that I have, even if I have replicated eigenvalues, that I have a unique eigenvector for even one of those, and then I have eigenvectors that match everything else. So that's just saying that I can write this decomposition. Okay? It looks like this, nothing too surprising. And again, if I have, say, lambda m minus 1 and lambda m are identical eigenvalues, I have to have two eigenvectors that are unique. Otherwise, I'm in trouble. But that can happen. They have to be linearly independent. This leads us to ideas of multiplicities. So algebraic multiplicities, it's just that number of times an eigenvalue repeats itself. So just repeating. Geometric multiplicity is defined as the number of linearly independent eigenvectors that belong to each eigenvalue. So if I have geometric multiplicity equal to 1, I can still have algebraic multiplicity that's greater than 1. That's fine. But it's just kind of talking about how many eigenvectors I have matching with eigenvalues. And that's where the idea of full eigenspace comes from. Okay, so give you a couple of minutes, figure out the multiplicities of this thing. They are zeros where there's no numbers. So hopefully this is somewhat obvious what the multiplicities are here and what the eigenvectors are. And recall very specifically what an upper diagonal matrix and a matrix times the identity has for eigenvalues. Okay, so I'll give you a couple of minutes for that. What are the eigenvalues for these two matrices? There are two. Both of them have 2s. And the algebraic multiplicity is 3 for that eigenvalue. Note the multiplicities are usually associated with a particular eigenvalue as well, because it's a little bit easier to talk about. So whenever you have an upper triangular matrix, it means the determinant can actually be determined by its diagonal. So you can do 2 minus lambda, and you get the characteristic polynomial very easily that way. The difference between these two matrices, though, is the fact that the eigenvectors. In this case, if we just put in 2 minus lambda, we end up getting basically like an unconstrained system for eigenvectors. We find out that the geometric multiplicity of the system is actually such that I get independent vectors. So the eigenspace is full in that case. The second one is not true. If I plug in the eigenvalues and try to solve back for the eigenvectors, I find out that they're connected, and I end up getting only one eigenvector. That's a linearly independent one. It's a multiple of the unit vector in the x direction. So B does not have a full eigenspace. It has a geometric multiplicity of 3 as well. So you have to be careful. Just because they have the same eigenvalues doesn't mean that they act the same in terms of the eigenspace. Okay, so let's talk about the eigenspace a little bit. So the eigenspace, especially for multiplicities of the eigenvalues, we can kind of talk about the subspaces that these eigenvectors are forming. And then inside those subspaces, then the multiplication by lambda is going to give us some special properties. Okay? So say I had a lambda and only an eigenvector associated with that lambda. The subspace is just going to be that one-dimensional subspace. And anything that's in that subspace, only in that subspace, is going to be acted upon by the matrix A by multiplying by lambda. So the component in that direction is going to be expanded by lambda. So this is really saying that if for a full eigenspace in particular, that it's going to make a bunch of subspaces in the overall space where the action that A is taking is just going to be like multiplying by a scalar, which happens to be the eigenvalues. Okay, so that's really the power of finding the eigenspace. We're dividing up the total space into pieces and understanding what's happening in those particular spaces altogether. In the case, again, if we have an algebraic multiplicity, but we still have a full set of eigenvectors, it's still a subspace. It just means we're in this bigger space that we can still multiply by lambda and get the same thing out. Very similar. In the case that we do have a geometric multiplicity that's 1, we call this non-defective, and if it doesn't have a full eigenspace, we call it defective. So these are just different terminologies for very similar type of ideas. Just one other quick thing. 2 important pieces of a matrix are the determinant. We know the determinant determines if we have an inverse and things of that nature. And the trace is the sum of the diagonal. So actually it turns out that that can be very important as well. We can get these actually directly from the eigenvalues of the matrix A. So we're going to actually relate this to various properties of A. But the determinant of A is the multiplication of all the eigenvalues. So it's the product of all the eigenvalues. And hence why if A has a 0 eigenvalue, you have a 0 determinant, which means you don't have an inverse, because you have to divide by the determinant in order to find the inverse. The trace is the sum. So the sum of the eigenvalues gives you the trace. Okay? The trace is often used in trying to describe if the matrix is diagonally dominant, which can have important consequences for things like optimization and things of that nature. Okay, so we saw there's a decomposition. Let's abstract that a little bit and talk about something called a similarity transformation. If we say A is similar to another matrix, then we have some transformation x inverse times A times x, that other matrix is similar to A. And the key part of being similar to A means it has the same eigenvalues. So if there's some sort of transformation like this that exists, then we say those 2 matrices are similar. Okay? Now, I do want to back up a little bit here, point out that that is a similarity transformation. The matrix A and the matrix sigma, or lambda, excuse me, are similar to each other, which is not surprising because if that has the diagonal to be the eigenvalues of A, then of course this thing has the eigenvalues that are identical to A. So this is, in fact, a similarity transformation. Okay? Now, all we really require for similarity transformations is that they have the same eigenvalues, though. This actually allows us to talk about a little about the multiplicities of the eigenvalues because we can actually map between 2 different similarity transformations. So that's actually where this statement comes from. The algebraic multiplicity of an eigenvalue is at least as great as its geometric multiplicity. This means that in order to have a geometric multiplicity, you have to have an algebraic multiplicity. It's not too surprising, and you can show this using similarity transformations. Okay. Sure factorization. Yet another factorization. It's a little bit different than we've seen before. We say Q times T times Q. T is upper triangular, so it's not R particular. Q is a unitary matrix or orthonormal matrix, okay? And we can decompose A into these things. Now, because Q is an orthonormal matrix, this is a similarity transformation. This means that the eigenvalues of A and the eigenvalues of T are identical, okay? And in fact, this is great because we can read the eigenvalues of T off the diagonal. So this is a little bit better. We don't have to get the thing to be a diagonal matrix. We just need to make it upper triangular. Okay? This is starting to get towards being able to compute these things. Okay? If we can figure out this decomposition and get this thing to be an upper diagonal, upper triangular matrix, we've solved the eigenvalue problem at that point. Okay? So that's great. We have Qs. We learned how to compute Q, or something that's Q. Note that this isn't a QR factorization yet, though. It is going to be related eventually. But we do want to construct something like this. Oh, I just said that. This is the important point, though. Every matrix A has a sure factorization. Not every matrix has an eigenvalue decomposition. We can't get that good. That was also similarity transformation, but we can get a sure factorization. Okay? So that's great. That means that we can actually do what we want. And there's some equivalent statements that we'll end with today. An eigendecomposition, so x, lambda, x inverse, where the x's are the eigenvectors, that exists only if and only if A is non-defective. So that means it has a full eigenspace. Okay? Otherwise, we don't have enough x columns. Doesn't work. A unitary transformation, or a unitary transformation like this. So the unitary transformation is going to be something that has the eigenvalues in the middle here. So the difference between sure and a unitary transformation is going to be that that's a diagonal matrix versus a tridiagonal matrix in the sure factorization case. What happens in a unitary transformation? That just means that A is normal, not in like, normal people sense. It's normal in the sense that A star A is equal to AA star. So in some sense, it's normal to itself. So that does exist. And that's actually nice because then we have some properties that we can exploit. But we still know that a sure factorization always exists. And this is the general case that we're going to be aiming for. So note that each of these things we're going to find by trying to find the sure factorization, but we're actually going to get a little bit more if we have these special properties. Okay, so I think I'm going to stop there today. We'll start back up next Tuesday. Have a good holiday. Next Tuesday, we'll probably get a ways through the rest of the eigenvalue stuff and maybe start on iterative things. Which will also form the eigenvalue stuff, and iterative things are going to form the last homework. So look forward to that. And I will see you in a week.